So we're going to start off with Toby Burnett introducing Bea.
Hey, hello everyone. I'm happy to introduce my mentee, who did very well. We had a lot of fun this summer, and I'm hoping that to do more in the future. But anyway, so here she is, Bea Schubert. Take it away, Bea.
Okay, I'm going to share my screen real quick. Do I just go or should I be told when?
You could go into presentation mode with your slides.
Oh, yeah.
And then just start going.
Okay, cool. Hello, I am Bea Schubert, mentored by Toby Burnett, and over the summer, I have been analyzing Olbers's paradox through Fermi's lens. We are going to begin with the background. The Fermi Gamma Ray Space Telescope was first launched a bit more than 17 years ago, and it uses a specialized lens to observe gamma ray point source populations. The point source populations that I will be looking at are blazars, pulsars, and millisecond pulsars. Blazars are galaxies with an active galactic nucleus that emits matter at high energies, causing brightness, while pulsars and millisecond pulsars are both neutron stars emitting radiation, also causing pulses of brightness. And then what is Olbers's paradox? In 1823, famed astronomer Heinrich Olbers asked a very simple question that many people don't think about. In a static universe that is both infinite and ageless, why is the sky not filled with stars? It's because one of the three assumptions made must be false. The universe is either not ageless, not infinite, or not static, or a mix. And what are the common solutions to Olber's paradox? There are two. There's the flux form, which I'll be focusing on today, and the line of sight form, which I do not have time to go into, unfortunately. The flux form is based on the inverse square law, that light from further away becomes less intense and more distributed. So if you're looking at a very far away star, its light is distributed around so much space that it's really hard to see. And just to define flux, flux, also known as apparent brightness, is the luminosity over 4 pi times the distance squared. It's important to take note that the only variables to the flux are the luminosity and the distance to the point. It's also incredibly important to log n log s distributions, a cumulative source count distribution model. And to go further into log n log s distributions, these distributions are used to view the cumulative distribution of a number of sources n brighter than a given source. It's a test often used to analyze the relationship between distances and apparent brightness, and it's often used in determining the viability of newer cosmological models. If your proposed model doesn't follow this distribution, you know something is probably up. And the first thing I did was a simulation. In order to visualize what a log n log s distribution would look like, I simulated it in Python. I did this by generating 30,000 points within a cube, and then integrating a sphere from said cube. From that sphere, each point on that sphere became a certain star in the universe that I could measure the distance to. Also important to note, in the simulated universe, every object has the same luminosity, 871 solar luminosities. That is just because that's the luminosity of my favorite star, Beta Cantor 3. This means that the only thing that will cause differences in flux are the distances to the points, so we can get a better idea of how distance impacts it. And this is the final result. I was able to take the natural logarithms of the flux values and the logarithms of the number of points brighter than a given value, and it created the distributions seen here. Also, the expected slope, -3/2, comes from algebraic manipulation of the proportions between the flux and the area of a sphere, the volume of a sphere. So our expected slope extending into infinity is -3/2. And then we move on to real data. From Fermi, we have a data set from over 16 years of its observations. The dataset includes blazars, pulsars, and millisecond pulsars, including a few other things I did not focus on. As you can see, the blazars and millisecond pulsars mapped out on these ATOF projection maps are both generally spherically distributed, but the pulsars stick to a flat plane. This means that while the blazars and millisecond pulsars maintain the -3/2 slope, the pulsars maintain a slope of -1. Also, special thanks to Professor Burnett for generating the code that allowed me to map this. And on the left, there is a summary of the 16-year data set in CSV form showing the object, its location, and its log S value. Because I had the log S value, I only need to calculate log N. This was done mostly using pandas data frames in Python, and I was able to create 3 graphs from this data set, each showing a different distribution. You can see my 3 graphs here. On the furthest left, we have the blazar distribution, with it lining up pretty well to its expected slope of -3/2, excluding a bump at the bottom. The millisecond pulsar distribution also lines up pretty well with -3/2. It has a minor bump in the center, but otherwise it is mostly aligned. And the pulsar distribution does align pretty well with the expected slope of -1 because it is plane. And to analyze it, we know that the blazars have the smoothest slope because it had a much larger sample size to choose from, so the line was able to get smoother. It was a sample size of 400 compared to 4,000 compared to things in the high hundreds. And also, each graph plateaus at the beginning. This is because at a certain level of faintness, Fermi detects all of the objects as the same level of faintness. So the first few points are all the same brightness for Fermi's observations, thus creating the flatness. And in conclusion, we can summarize that the blazar and millisecond pulsars both approximately follow what is expected of a sphere. Meanwhile, the pulsar distribution follows the expectations of a plane, meaning that they're evenly distributed across the galactic plane instead. Also, we know that as distance increases, stars get increasingly faint. The expected slope of a log N log S distribution in most cases is -3/2. Olber's paradox argues that the sky cannot be dark if the universe is infinite, ageless, and static. And, of course, the number or age of the sources is irrelevant to individual flux. As evidenced by all of that, we can successfully conclude that the sources of gamma ray light in the universe are evenly distributed across said universe and contribute as expected to the brightness of the sky. However, that brightness is not nearly concentrated enough to be visible to the human eye, thus maintaining the darkness of the night and confirming the opposition to Olber's paradox. And to wrap it up, I learned a lot, both from this project and the research leading up to it. I know that I became very proficient in Python, and I was able to learn how to read and analyze academic research. Most importantly, though, I learned how to properly communicate and work in an academic setting. I really did become so much more passionate about the science because I was genuinely able to have a hands-on experience, and I'm really grateful for that opportunity. And of course, thank you so much to Professor Burnett for mentoring me through this internship. I've had some challenges that he helped me through so much, and it's really been an amazing experience.
All right, let's clap for our speaker. Great job, Bea.
Amazing.
Thank you.
Does anyone have any questions for Bea?
I guess I have a question, B. Where do you see yourself going with this project? Do you think you're going to stay with it in the long term, or did it just open new avenues and you want to explore more? What are your goals?
I think it opened a lot of new avenues. Like, I'm very interested in following the same type of research, but in a broader sense, looking at how it branches off, kind of.
Great, thank you. It's great talk.
Yeah, a fun simulation to try next would be to try varying the brightnesses of the stars and seeing how that affects things.
Oh, wait, did you want to add why you chose the specific luminosity?
Oh, no, she said, she
Oh, you
said it.
said, I just wanted to remind everyone.
Really great job. Beautiful slides and excellent, excellent work.
Thank you so much.